All right, good afternoon, everyone. I'm Cheyenne Jones. I'm the PR and Marketing Specialist here at NRWA. Thank you all for joining us. Today we have Zach Barkjohn and Joe Dreyer from Xylem presenting non-revenue water, matching the right tool to the right job. Following this session, you will receive a certificate of completion and a copy of the recording. Please allow at least 24 hours to receive these materials. If you're watching this as a recording and you need a certificate, please email me at cheyenne@nrwa.org. Attendees will be muted during the presentation, but please enter your questions in the question box to the right, and I'll answer any technical issues, and any other questions will be answered at the end of the presentation. Thanks again, and I'll turn it over to Zach and Joe.
Thanks, Cheyenne. Welcome, everyone. Good day to you all. And thanks for joining us for our presentation entitled Non-Revenue Water, Matching the Right Tool for the Right Job. I am Zach Barkjohn, and I'm presenting this with my coworker and friend, Joe Dreyer. And as engineers at Census, we have the pleasure of working with a lot of utilities. I hope that some of the utilities we work with are on the line today, primarily in North America, and we use technology to address non-revenue water. It's really what we're trying to accomplish today is really just give a primer on a lot of the different technologies available to you and kind of where they fit in the overall program. But before I get started, I wanted to tell a little story. The year was 1857. It was a few years before the American Civil War began. And the SS Central America is a side-wheeled steamer carrying roughly 600 on their way back east with their fortunes made in the California gold rush, a fortune that included 30,000 pounds of gold. En route from Panama to New York City, this ship, found itself in a hurricane off the coast of the Carolinas. And after a couple days of struggling to survive, the ship sank, taking the majority of its passengers with it and all of that gold to the ocean floor. Out of those 600 people, only 125 survived. It's considered one of the greatest maritime disasters in American history and contributed to the financial panic of 1857. And this ship lay there untouched for over 100 years. That is until Tommy Thompson came around. So Tommy was a real engineer's engineer, and he was interested in deep sea exploration. Right out of school in the 70s, he began working with treasure hunters in the Caribbean. And these treasure hunter operations were fairly simple. They used scuba divers to search areas around the shallow reefs and sandbars. It's almost more hobby than actual career. The problem with this approach, though, is that many ships had sank in the Caribbean waters, so you'd be uncertain if the debris you found diving was related to the ship that you were looking for. These wrecks would have been shallow enough to recover, so the treasure might have already been gone. At this depth, the storms and currents could break up and move the wreckage, depositing that wreckage under many feet of sand. So this just made diving and looking for treasure really, really difficult. From the book on this subject by Gary Kinder, referring to Tommy Thompson, he said he began to see a pattern. They operated from day to day with no long-term plan. They were all underfunded, no one kept accurate records, and the turnover rate of workers was high. So you might get some clue on why I'm telling this story now. So Tommy began to approach treasure hunting in a more systematic way. He realized that in order to be successful, he needed to hedge his financial risk. He collected historical accounts for shipwrecks, including survivor accounts, committee testimonials, captain's logs, cargo manifests, weather reports, all sorts of things. He started studying the environmental conditions of the ocean. He understood that if he could understand how the currents were moving, he could understand where the wreckage might lay. So he studied the environmental conditions, mapping the currents, the depths, the sedimentation patterns. He utilized sonar in a way it had never been used before to verify the presence of likely targets. And then at the final end, he used advanced robotics to verify the exact location. And jumping to the end, after 5+ years of hard work, he located the SS Central America and recovered roughly 1,000 pounds of gold. And so I tell this story because it's a good analogy to water loss. The difference being, as we all know, clean potable water is much more valuable than gold. And so the question becomes, how can we apply a systematic approach like Tommy Thompson to minimize non-revenue water? Tommy recognized that the old school treasure hunters were just jumping straight to the scuba divers, the most precise but the most labor-intensive endeavor, without first doing their homework. And so for Tommy, his work started with researching historic documents. He wanted to confirm that there was enough documentation of the shipwreck to sufficiently restrict his search area. After all, he couldn't search the entire ocean. Similarly, the AWWA water balance requires collecting data from a variety of sources to get a better understanding of water loss in the entire water system. The main point here is that the water balance, or the water audit, you'll hear it called both things, helps utilities understand the magnitude of water loss and the uncertainty in those calculations. And understanding this is extremely important for deciding the correct mitigation. And so while we're primarily focusing on real losses today, if the water audit or the water balance points to apparent losses being a bigger problem, there are meter testing programs and data science techniques that can be systematically deployed as well. So focusing on real losses or leakage, the optimal level is non-zero. So Tommy was looking for ships with enough documentation that he could narrow his search to a reasonable size. With that criteria met, he looked for ships that had records of valuables being transported. It was through these two criteria that Tommy and his team began focusing on the SS Central America. This is another way Tommy was mitigating financial risk. He wanted to make sure that the juice was worth the squeeze, to borrow a term from one of my coworkers. And similarly, the economic level of leakage is a tool we can use to determine what level of leakage is worth achieving system-wide. And so the idea, the economic level of leakage, is illustrated by this graph. So on the vertical axis, what I'm representing here is the cost. And then on the horizontal axis is water loss. And so if we think about it, we're kind of where we start today. The cost of water is that downward sloping line. The more we reduce water loss, the less cost that lost water. Makes a lot of sense. However, reducing non-revenue water isn't free. We have to do some sort of leakage control. We have to take some sort of mitigation. And so that leakage control, it's a lot easier when you have high loss to go out there and find leaks. It becomes a whole lot harder when you're already at a very low leakage level. And so that's why we see the kind of the exponential rate up. And so what we want to consider is not just the cost of water, not just the cost of leakage control, but the sum of those two. We want to be minimizing that total cost. And that's where we want to attack. And so consider a leak that causes a sinkhole in the middle of a busy street in the central business district. This is likely a higher priority than a small leak in the forest because of the cost to remediate and the cost to your town. But Tommy didn't stop here. He started going out and looking for the ship. He began compiling the historic data in what started as a really big matrix on his wall and ended up in as a Lotus Notes database. And for us, that's a lot like keeping a good GIS record of our assets and the repaired leaks or bursts. But the historic data is only one side of the equation. Tommy realized the ocean is a very dynamic system, just like water distribution systems. He used ocean science to study those currents and that sedimentation patterns around the areas of shipwrecks. We too can use a distributed monitoring approach to understand the dynamics of the water in our distribution systems. Depending on where you are, distributed monitoring can be achieved in a few ways. Utilities that have implemented advanced metering infrastructure, or AMI, for billing collection are an advantage because not only does AMI provide granular and rapid consumption information, it can also be the backbone for information collection. So it's all about getting more out of the infrastructure you already have. So for those of you who may not be super familiar with AMI, an overview of our particular AMI infrastructure is illustrated on the right here. Radio towers communicate with distributed devices, meters, sensors over a communication protocol that was designed specifically for utility grade battery life and operations. And so although it's not technically a part of the water balance, a nice benefit of this AMI system is it can be used to alert customers of customer side leaks. So this can have a couple of good benefits, from improving customer relations and minimizing bad debt. So at this point, I'm going to turn it over to Joe to explain a little bit more on how this applies for our customers.
Thanks, Zach. So yeah, to illustrate this a little bit more, I wanted to introduce a case study. And the case study I'll present here is for Etowah Water and Sewer Authority. They're located about an hour north of Atlanta. And this particular utility has about 5,400 service connections or customers. And it's responsible for delivering about 1.5 million gallons of treated drinking water every day through nearly about 175 miles of distribution piping. And a few years back, they actually went about replacing their entire meter base. They had aging meters of all kinds from multiple different manufacturers. And so not only did they want to replace those meters, but they also wanted to implement an AMI system, as Zach was mentioning, that's advanced metering infrastructure. And what they want to do with that is get a system that would meet their measurement, communication, and analysis needs for the years to come. And so what this new system provided them with is hourly resolution consumption data for all of those service connections, all those customers. And the utility saw a lot of benefit from that hourly data, not just on the system side, but on the customer side. And so one thing that they have in place is a usage portal, a customer portal. And what that allows their customers to do is kind of log in and see their water usage. It allows them to conserve water, detect leaks, receive alarms, and just overall understand their bill better. And so that's definitely a benefit in terms of customer service. But with this solid system in place, one thing that they observed is that the overall success rate of readings was quite high. And as a result, they didn't have to do read estimates as much, so that was reduced. The other thing that they saw was a 5% increase in revenue without a rate increase. And so that was resulting from improved meter accuracy, particularly on those large customers that can sometimes account for a larger share of the total consumption. And so, these two benefits basically resulted in a reduction of the apparent losses in that non-revenue water balance that Zach was just talking about. So the return on investment from that can actually be used to help fund the next steps towards finding and addressing non-revenue water. In other words, if you had some old inaccurate meters out there and you're able to either test them or replace them and recapture that revenue, that can actually, in addition to reducing the apparent losses, that can actually be a financial benefit to help you take the next step towards additional technologies. And so one thing that Etowah actually said, as you can see on the slide there, is that their customers trust them to make really solid decisions about limited water resources. And so to illustrate that a little bit and to see how this AMI system helps them do that, let's say, for example, that there's plans for a new factory to be built on the far side of town. And you want to answer the question, are we going to have a sufficient supply of water to meet the demands of this new plant? And that really brings to light one of the most important benefits to this hourly consumption data, because it can be used for better modeling and planning. So for example, you could actually take demand profiles of certain service types, maybe residential versus commercial, certain zones or certain DMAs. You can take those demand profiles and feed them into the hydraulic model to provide better demand inputs and improve the model accuracy. And I think the bottom line here is that, this network, let's refer to it as a smart utility network, provides basically a foundational system for data collection and monitoring. And having accurate and complete water balance data is really the first step to determining the levels of loss in the water system. Once you have that, then you can move towards those more advanced techniques and methodologies for addressing non-revenue water. And Zach is going to go into some of those in a bit here. And so let me turn it back over to Zach to talk a little bit more about monitoring other parameters through systems like this.
Thanks, Joe. So as I mentioned, we can use AMI for a lot more than just meter reads. And in fact, Joe brings up a good point. At this point, we should not be necessarily calling it AMI, we should be calling a smart utility network because it does capture more than just meter reading. And one application for that is pressure monitoring and management. Leakage is a function of pressure. The higher the pressure, the more background leakage that occurs. You think about it just like a hose. There's an orifice in the pipe, and the more pressure you have on it, faster it's going to flow out of that hole. So additionally, aside from that background leakage, breaks occur when pressures exceed the tensile strength of that pipe wall. Reducing pressures means that we can reduce breaks as well. So it comes to stand that the lower we can keep pressures, the less water loss we'll have. But, and this is a big one, there is a limit to this. If we go too low, we could see an increase in customer complaints, or even worse, create an environment where back pressures can introduce contaminants. So it's because of these concerns that monitoring pressure is an important component of pressure management. Fortunately, battery-powered devices such as smart water meters with integrated pressure sensors, I've got this Ally shown here that has that integrated pressure sensor, can be deployed in a really cost-effective way to monitor an entire system. Especially when we're talking about it being integrated in a water meter, there's no civil work involved in there. You already have to have a water meter in place. So really the cost is the differential cost between that meter and the meter you would already have in that hole. So I'll talk a little bit more about sensor density in a little bit, but at a minimum, monitoring at the lowest and highest elevations per zone is crucial to pressure management. And I'll let Joe cover another case study.
Yeah, thanks, Zach. So this next case study is in Washington State. It's the city of Walla Walla. And this particular utility finished deploying a Census FlexNet AMI system a couple years ago. And basically they have this network of 2 collectors, we call them base stations, and those receive hourly readings from about 10,000 metered service connections. And so with this new system in place, Walla Walla saw a lot of those benefits we talked about in the last case study, like reduced read estimates, improved meter accuracy, and enhanced customer service. But they didn't stop there. They said, you know, we want to focus on how else can we leverage this network to do more. And one problem that this city faces is pressure management. The whole water system is basically a sloping hill from the northeast corner of that map down to the southwest corner. There's a whole lot of elevation change. And so what they have is 25 pressure reducing valve stations, or PRVs, and those regulate the pressure in 4 different pressure zones. And so they're kind of like slivers on the map, knocking the pressure down from one zone to the next. And without any pressure monitoring in place past the treatment plant, they really didn't have any visibility into the behavior of this water system. And so oftentimes they'd get a customer call, and that might be actually what alerts them to a condition like low pressure, high pressure, or maybe a failing asset, like a failing PRV. And so through Census, what they decided to do is leverage some of those products that Zach had in the previous slide to start monitoring pressure, and to do that using the network that they already invested in. And so what they did was they created a plan that consisted of about 100 points all around the system. And they actually got pretty strategic with that pressure monitoring plan. And so as Zach mentioned, you know, the highest and lowest points in each pressure zone, but they also looked at some of the critical customers like hospitals and schools, and the critical assets that regulate the pressure, like the PRVs. And on the slide here, you can actually see that plan and some of the examples of the installation. So in the upper right, that's an example of a PRV site where they added a pressure sensor to the upstream and downstream side of the regulating valve. And they wired both those sensors up to a smart gateway, which is basically a radio gateway that reads sensors and operates on that network. And then in the upper left, you can see a large meter. This could be an important customer, maybe an industrial plant or a hospital. And there's a pressure sensor in the test port. And so they have that wired in so they can have a pressure reading right there at the service connection. And then on the lower left, you can see one of those residential meters with the integrated pressure sensor. It's the Ally. And that really constitutes the bulk of the points that are distributed around the system, kind of for the reason that Zach was mentioning before, where there's a little bit less, in terms of the installation cost. It's just easy to swap out the meter and get a pressure data point there. So going on to the next slide there, all this pressure data coming through these devices over the network, and the question is, what do we do with it, right? You have all this data, you need to actually get some action out of it for it to be worthwhile. And so the solution to that was the software application that Census has called Pressure Profile. So it goes into that analytics application. The utility makes their groups for different devices. They can trend out the pressures, set up alerts and alarms, and map it all out. And what you're seeing on the slide here is actually a 1-month view of the pressure profile in their 4th pressure zone. So that's the bottom pressure zone. And what they saw was that there was a whole lot more variance on a day-to-day basis than they really would have expected. So you can see on the slide, at a single point, right, one pressure sensor, they were seeing pressures ranging from 85 psi all the way up to 135 psi. And so not only was the pressure higher than they expected, but the variation of the pressure was much greater than they expected. That large variation in pressure, if it keeps repeating, that can be a fatigue stress on the pipes and the other assets in the system. And fatigue stress eventually can lead to failure. And the other thing is that the higher pressure, as Zach was mentioning before, with the, thinking about a garden hose, higher pressure, higher leakage rates. And so what they knew right off the bat here is that they had some room for pressure stabilization and pressure reduction. And those two methods are actually cited in the AWWA M36 manual as being effective pressure management methods for mitigating real loss and leakage. And so basically what we're saying is turn down the pressure and stabilize the pressure if you can do that safely in order to reduce that background leakage. Now, the graph also shows something there towards the right where it says PRV failure, stuck in closed position. This brings up more of an operational benefit to pressure monitoring. And so what is that big dip in the pressure? Well, that's actually one of the pressure reducing valves failing in the closed position. This basically resulted in an entire area of the system losing pressure. And the interesting thing about that is that the operators at the treatment plant didn't see the tank levels drop. And the reason they didn't see that is because the valve was closed. And so it wasn't as though there was a leak or a major break. There was just an area that was basically shut off. It wasn't draining the tank. But what the utility was able to do was get an alarm from the pressure devices in that area, see that pressure drop, and then alert their crews to go out and resolve it promptly. And more importantly, resolve it proactively, maybe before you have customers calling in, or maybe you're able to address that and fix it, or at least notify them that there's a problem, right? It's kind of nicer to say, well, I'm going to call you about a problem I know about, rather than having to, hear about it from the customer. And so last part of the graph there brings us back to pressure management, looking all the way on the right side where the pressure is starting to drop and be stabilized. And what that is the utility actually adjusted their PRV set point. And what they did is they smoothed out and lowered the pressure. And so by monitoring, through that zone, they were able to confidently evaluate those changes made and ensure that there was no disruptions occurring. So for example, if they had done pressure management, reduced the pressure, they could have been concerned that the pressure would be too low in a certain area. But because they had these distributed monitors and because they could see it every hour of the day, they were really confident in their approach. They're not just blindly lowering the pressure, but rather, they know the pressure everywhere. and they're confident that the changes they're making are not going to disrupt service. And so now they're looking at how to do the same thing in other pressure zones, and they're expanding the number of monitoring points as well. And the other thing that this utility is doing with pressure data, and I find this really interesting, is that their utility engineer is actually comparing the pressure readings that they're getting to the output from their hydraulic model. And they're using that information to detect valves that are in the wrong position. So for example, like system valves that are closed but shouldn't be, and also PRVs that aren't set properly or aren't performing properly. And so I'm going to turn it back over to Zach now to talk more about DMAs and some of the water loss methods with district metered areas.
Thanks, Joe. Yeah, every time we talk about pressure, I feel like there's one more thing that's really fun to talk about. But getting back to the story with Tommy, so in his quest for treasure, Tommy Thompson distilled all that historic and environmental data into a Bayesian search grid. And so that's what that white graph is there on the screen. And this really isn't too dissimilar from the concept of a DMA. So in Tommy's case, what those numbers are representing is higher probabilities of, he thinks, the wreckage is in those locations. And so when he goes on the next step to actually going out there and searching for it with sonar, he knows which areas to prioritize. DMAs do the same sort of thing. They help us narrow our focus. They help us segment the network into manageable zones. They quantify the impact of interventions. They monitor and quantify water loss. And so with AMI in place, you can perform this water balance at a more granular level temporally as well as spatially. This allows us to then focus on which technology to apply in which zones. We don't necessarily have to do the same thing to each zone, because that probably is not the most effective approach. And of course, for this approach, district meters are required. DMAs are definitely a lot more popular in Europe than they are here in the US, but that's changing. We're realizing the value of being able to segment up the network. And traditionally, DMAs are sized to roughly 2,000 service connections. And so essentially what we're doing when we're talking about a DMA is installing a district meter. And one of the reasons why they just haven't been super prioritized is because the costs associated with that. But now with insertion meters, we can install those district meters in a much more economic way. The other thing to think about too is that although we would generally size these to 2,000 service connections, that can be a bit difficult to implement just because of the number of meters we would need. But we shouldn't necessarily let perfect get in the way of better. We can create DMAs in particularly critical or troubled areas, or we can use the natural network topology to minimize equipment. There's a lot of things. And I won't go too much into this because if you go on YouTube and you search for the USA utility case study, NRW and small systems, you'll find a really great presentation recording by Chris Luber on his experience with DMAs. It's really good. I'd recommend it. So now I'm going to turn it back over to Joe to talk about another one of our customers who's using DMAs.
Thanks, Zach. So for this example, we're going to go down to Dallas, Georgia. And what this example really highlights is that AMI can be a really good tool for building out or supplementing the approach that a utility has towards district metered areas. And so in this example, Dallas already had one larger area of the system set up as a DMA, and they had master meters there, and they were on a SCADA system. And they had all their bases covered with the residential and the commercial accounts metered through census products and going up to the AMI system. And then they also had their master meter, and they were able to do that water loss calculation. But the problem that they had is they also had a bunch of smaller DMA areas that they wanted to create. And those were more on the outskirts of the service area. You can see them on the map there as kind of the smaller polygons. And for this, they really required a solution that could be cost effective and easy to implement. They wanted to have something that would be battery powered and running on the same network that everything else is already running on. And so what they did was they connected master meters for these smaller areas via the AMI system, using the AMI system. And going on to the next slide there, the higher resolution time data, and when I say that, I mean like the hourly reads from the AMI system, really makes a difference when it comes to DMAs. And instead of doing a water balance on, let's say, a monthly time scale, you can actually bring that down to a week or a day or even a few hours. And in this example that we're seeing here, Dallas found that one particular DMA, one of those smaller ones that they had set up over the census network, showed an inflow volume of about 100,000 gallons and an outflow volume of about 57,000 gallons over a 48-hour period, about a 2-day period. And so there was this 50,000 gallon discrepancy, which was way out from the normal difference they would see. And so they said, all right, this is due to either unauthorized consumption or a leak. And so right then they dispatched a crew and they did find and repair a leak. And then what they did was they validated that repair by looking at that DMA data. So they saw the inflow and the outflow. They saw that they were again closer back to the range where they should be. You can see in the plot there, the red box is circled around the 48-hour period with the discrepancy, and then after that it comes back into normal. And so what this is really allowing them to do is use DMAs as a tool to subdivide the system and get a better picture of the losses in each of those DMAs. And AMI for them was really a key tool to bring back that data and get kind of a scalable, feasible solution to continue to build out their DMA strategy, whether that's subdividing DMAs that are there or adding new ones. And when you find those higher levels of losses, now it's time to get more targeted in your tools. And for that, I'm going to turn it back over to Zach to talk about, how do we use technology, more targeted techniques to address higher levels of leakage that can be identified through DMAs or pressure monitoring.
Yeah, exactly. So once Tommy and his team had their search grid that I showed prior of the likelihood of the wreck of the SS Central America, they employed a much more precise technology. In their case, side scan sonar. Sonar would tell them of anomalies on the ocean floor that might be the wreck. So this is analogous to more precise monitoring equipment used in water distribution. These technologies include acoustic loggers such as hydrophones, which sit in the water column themselves, or accelerometers, which sit external to the pipe. These are both great technologies for monitoring growing leaks or new leaks. And another type of technology is transient pressure sensors. These are really ideal for monitoring for breaks or bursts because they're going to release that transient wave. And while transient pressure sensors are not necessarily going to help control for water loss, they're much better for public relations. Like Joe was mentioning, it's a lot better to be able to call the customer and say, hey, there's a problem in your area, rather than the other way around. Additionally, the transient pressure monitors can help identify any transient loading, which can reduce the asset life. Just like Joe was saying with fatigue stress, even if those are daily fluctuations, think about if it's transient fluctuations that are occurring in fractions of a second. Can add a lot of stress to your pipes. So these technologies are really best suited for permanently deployed situations, especially on the transient and the hydrophone side. This is really good for those critical areas such as your downtown or areas with repeat failure, maybe at the mayor's house. But alternatively, these technologies are also useful in deploying in lift and shift scenarios, especially when you don't necessarily want to invest in a really high density of sensors all across your system. instead targeting DMAs that are showing the largest leakage. Another technology kind of in this vein is not so much a technology, but rather a technique known as the step test. This is kind of an old-fashioned method. If you watch Chris Luber's presentation on DMAs, he covers this. And essentially, this is just closing valves and registering flows at the district meter to focus in where the leak is. But finally, when we're talking about sensors, and even staff time, to be fair, we must balance the sensor cost and the efficacy. So Tommy realized that there was a financial risk to using the side scan sonar more than it was needed to. He had to rent the ship, he had to rent the crew, it was very expensive. So he had to be very precise on where he targeted it. And so similarly to that, there's a trade-off between sensor density and precision. That's what I'm showing here on that graph on the bottom left. We can increase sensor density, and we can increase, by doing that, we increase precision, but it's not just perfectly linear. We have to find the right density of sensors in order to get the best bang for your buck. And unfortunately, this isn't a one-size-fits-all type of decision. You have to weigh in things like your own staff time into those sorts of analysis. But the main thing here is that we want to find an effective spacing of sensors that's going to help us focus our effort for our leak detection technicians. So that way they're utilized the most effectively. And I'll let Joe cover another example about this.
Thanks, Zach. So what we've got on the slide here is an example for you on a hydrophone, which is basically a high-frequency acoustic monitoring tool. And the plot that you're seeing there on the slide shows the system pressure, that's the bluish line that's trending kind of fairly steadily along there. And it also shows some green data lines that appear to be growing in magnitude. That's the acoustic noise from the hydrophone. And so the hydrophone is picking up a growing level of noise over a period of about 3 weeks, from about late October to early November. And in this case, Xylem, specifically the Vicente business unit, had a monitoring team that was checking this data and alerted the utility of this growing likelihood of a leak due to that increasing acoustic noise. And the utility rolled a truck and they made a repair in that area. And as you can see in the plot, the acoustic noise drops back down. But only about a week or two later, the noise starts increasing again. And the utility actually went back to the same area. They found another issue. The noise dropped back down. And so the bottom line to emphasize in this case is that permanent monitoring really made these findings possible. A one-time survey, can find leaks, and one data point, it doesn't really tell you as much as a time series of acoustic noise, which can allow you to track for that increasing magnitude to show a growing leak. And it's really quite similar to the pressure monitoring cases that we were talking about earlier, where a one-time gauge measurement, it does give you valuable data, but not nearly as much so as an ongoing monitoring solution that gives you near real-time data. There's a component here to not just identifying the problem, but also validating that you've addressed the problem, and that comes by continuing to monitor after that change has been made or that fix has been applied, and validating that the system is returning back to the normal behavior. If you think about the automotive manufacturing world, they have this culture of continuous improvement, and the last phase of that continuous improvement methodology is called control. And so I think about ongoing monitoring as really critical to that control phase, right? We've made our improvement, we've fixed the leak. How are we going to actually monitor that fix is still applied and that we don't have another issue pop up? And that's what this is all about. So I'll go ahead and turn it back over to Zach to wrap up here and conclude us with the presentation.
Thanks. Yeah, that's I'm glad you brought up that example, because I hear from utility operators all the time about chasing the tail of a leak. It seems like they fix one leak and another one pops up in the same location. And so it's those types of applications that I think the permanent monitoring is really applicable. You don't necessarily want to just blanket cover your system with acoustic devices that probably wouldn't get the bang for your buck that you're looking for. But in those areas that are really troublesome, they can provide a lot of insight that, as Joe mentioned, you just don't get from a quick survey or somebody going out there and take a look at it. So back to Tommy Thompson. He and his team used an unmanned autonomous vehicle to pinpoint the wreck of the SS Central America and recover that 1,000 pounds of gold. And for distribution systems or smaller diameter pipes, this is analogous to sending out leak technicians with correlators and ground mics. You know, I've seen very skilled technicians with just a piece of rebar and being able to use that as a listening stick. But this requires the most labor and the most skill. And for many utilities, their most skilled leak technicians are also their best foremen, just like Matthew in this picture here. It isn't just about where he spends his leak detection time, it is about how much time he can scrape together when he isn't being pulled onto other projects. For transmission mains or larger diameter pipe, external acoustic equipment doesn't work very well. This is where inline tools that either roll or swim through pressurized pipes are the most effective. They're effective because their sensors are literally inches from the leak in the water column. Typically, these tools are thought of as condition assessment tools due to their criticality, but there is certainly overlap between asset management and non-revenue water. If we think about it, they're really intrinsically tied at the hip. If we have really good conditioned, or if all of our infrastructure is really good condition, it's not going to leak as much. Similarly, kind of on the same side of the same coin is infrastructure that's leaking a lot is necessarily not in great condition. So reading this book, The Ship of Gold, that we've been referencing by Gary Kinder, I was really struck by this passage. The secret to working in the deep ocean was not in the technology where everyone else had been looking. Most of the technological pieces were there. They just hadn't been put together properly. The secret was in the concept behind the system and the interrelation of all of the subsystems. And of course, this made me think of the systematic approach to water loss, starting with a broad and historic view of the system with the water balance, trying to figure out your economic leakage level, and then utilizing AMI and smart meters to feed into that water audit, getting more high confidence in your measurement. Understanding those system hydraulics and improving the data set from that AMI system, and then leveraging that same AMI system to monitor and manage pressures throughout the system. Deploying more precise sensors when and where needed, and then finally deploying the most labor-intensive and precise tools to pinpoint leakage. And so when we're thinking about this, just to kind of reiterate, we want to be very systematic. We want to apply the lowest cost, most broad technologies, taking a historic perspective first, and then drilling down and really making sure we're focusing our efforts, focusing the higher cost technologies just where they are needed. So one more quote from Gary Kinder's book. Tommy wrote down 2 questions, and this was in the 1970s. By the year 2000, what kind of technology will be available to find and recover historic wooden ships lost in the deep ocean? And what prevents us from doing that at a reasonable cost right now? So it's now 2021. The technology is out there to address water loss. I think, what's keeping us from doing that today? And with that, I want to plug one more time this book. We're not authors. We've got no stake in this book, but I thought it was a really good read. If you've got an interest in water, you're obviously on this webinar. It's very interesting. And Joe, do you have any more comments? Anything I missed before we take questions?
No, just to wrap up, I think what we're trying to push here is a holistic approach to non-revenue water. Every utility is different, but I think following this methodology as kind of a primer for your approach could be beneficial. So I think with that we can open it up for questions. We got about probably maybe 15 minutes left here, so I guess we'll turn it back over and see if we have questions coming in.
We actually have a lot. I'm sure you guys can see some of these on the actual question box, and we've flagged some. Hold on one second. Okay. So do you guys want me to start with the questions that we talked about or the questions that the attendees asked?
Let's go with the attendees ones.
Okay, so in the city of Miramar, we have Census AMI. We would like to explore connecting the AMI data to our enterprise GIS water distribution network for improved workflows, analytics, and insights. We have Geo Events Server. Would you be able to send us any info on methodology to enable this sort of connection?
I can take that one. So what I would say in this case is we do have a professional services team, that works within the census business unit here that can help with those kinds of integrations, particularly when we're, standing up the system. A lot of the times we do get that ask to make connections to different third-party softwares. And that's where that team comes into play, just to understand what are the requirements, how often does the data need to be sent, and so on and so forth. And so typically they'll put together kind of a workshop to go through that and figure out the best way to connect to that other software. So hopefully that helps, but I would really encourage you to reach out through your local sales account development manager on the census side and kind of get started there to talk through the different options for making that connection.
Okay, are continuous quality control measures performed on the pressure and temperature sensors on Ally meters?
So
I can take that.
go ahead, Joe.
You want to take it, Zach? Okay, yeah, I was just going to say that, well, back when I was working in the manufacturing group, I did get to see a little bit, some of the quality control measures that go into the Ally meter. And so what I'll share with you is that I think what goes into that is more on the manufacturing side and the test setups that they have. I'm not sure if you've been able to tour any of the census facilities, but we do put a lot of effort into ensuring a quality product, putting it through simulations and tests with various different jigs in order to make sure that we're getting accurate and precise data. And so that would play into the quality control piece of it. In terms of ongoing readings that are occurring, I think your best bet there is just to monitor the data. You can set up alerts and alarms that trigger based on certain thresholds. We have seen one or two cases where you get a reading from an Ally meter and you say to yourself, this can't be right. Something's wrong with this piece of data. I don't trust the accuracy of it. And what we find most effective in that case is really to have a look at the other sensors in that vicinity of the water network and to look at that data and see if it tracks. If it does, it could be a real physical cause of that, let's say, a spike in pressure or a dip in pressure. And if it's not, then you might start to call into the question, the accuracy of the sensor and maybe go out with a gauge to check on it. We have seen some cases where, for instance, a valve was turned off and we detected that by the pressure dropping. We say, this can't be accurate for system pressure, but you go out there, you check it. Oh, looks like the curb stop is off for this residential address or something like that. So hopefully that helps give you an idea that what I would encourage you to do is go to our website and check out the data sheet for the Ally meter, because it has a little bit more information there about the specifications and accuracy for the pressure and temperature devices.
Okay, and what's the first step to get started in the NRW journey?
I'll go ahead and take that one. I would say that the first one is, if you haven't already, start with the AWWA water audit. They recently, just in the last couple of months, came out with a new software. It's essentially an Excel spreadsheet with macros built in. This newest update makes it really user-friendly. So if you haven't already played around with that, that's what I would recommend. Because if you don't necessarily have a good handle on the quality of data you're using to make these assessments, it's going to be hard to make the right decision. So definitely the water balance is the place to start.
Okay, how does apparent losses fit into the technology you just spoke about?
Yeah, I can take that one. So yeah, great question. Thinking back to some of my engineering classes from when I was in college, I had one professor that always used to say, garbage in, garbage out. And what he was saying there was basically you could have a great formula or a great equation or a perfect model, but if the data you're putting into it isn't accurate or isn't valid or isn't complete, you're really going to have the same on the outputs. So in terms of apparent losses, I think the same thing that's basically what we're talking about on the non-revenue water side of things. You can't provide an accurate picture of water loss unless you're confident in the accuracy of the measurement devices and you don't have data handling errors and these things that can impact those numbers. And so, I think fortunately there are some really good tools out there and technologies to address apparent losses. So for example, Zach mentioned early on in the presentation, softwares that can be used to detect meters that are slowing down or meters that are inaccurate or even meters that aren't sized properly for a certain service connection. And there's other tools like large meter testing devices that can be used to check the accuracy. And so without going too far into it, in a nutshell, that's how apparent losses can fit into some of the technologies and methodologies we talked about today.
All righty. So my staff is stretched too thin. How do I free them up to focus more on NRW?
I'll take that one. That's a tough one because, like I mentioned before, a lot of utilities, the people whose responsibility of being the leak detection technicians are often the best foremen dealing with larger emergencies. And so I think there's kind of two things you can go about it. One, there's always outside help. There's companies that Walks Water Service is one that will actually go and do these surveys for you. But again, you want to make sure that's within the right context. You're applying the right tool at the right time. So the way I think about it is, if you can leverage some of these other tools that don't necessarily take a lot of staff time. So monitoring, for example, utilizing your AMI system to monitor the pressure management. Not only does that give you a lot of information you didn't already have, but it really saves staff time. I know some of the utilities we work with talking about just monitoring pressure, they realized that before they were doing that, they were spending a lot of time trying to chase down problems out in the field because they just didn't have enough information. So they'd send a guy out to a site, throw a pressure gauge on something, or just get a look at the asset. Now with pressure monitoring, they can diagnose and figure that out without leaving the office. So it's tough without knowing all the particulars, but it starts with kind of leveraging technology you have, or by applying technology that might take a little bit of upfront investment, but will pay dividends down the road.
I saw one question come in here on ROI, and I thought that was a really good question. I wanted to take a minute to answer that. And the question is here, is a return on investment analysis performed to confirm AMI investment? And one thing I wanted to say there is, a lot of the times, the ROI analysis is done by the utility when they're investigating an AMI solution or any technology, right? Typically, that's where it's going to start. And what I've seen, at least with AMI, is oftentimes that analysis focuses mostly on the meter reading. So whether it's, reduced truck rolls, reduced read estimates, improving accuracy, improving revenue, and those sorts of things, that's really where it focuses a lot of the time. And so a lot of the R&I analysis that I've seen, ROI analysis, have not necessarily taken into account all of the other applications that can provide value, like the pressure monitoring or DMAs, and so on and so forth. And so I think it's really interesting. I think that ROI analysis should consider those other use cases that can be leveraged from, the smart utility network, so to speak. But yeah, just to tell you what I've seen, mostly it focuses on the basic functionality, the hourly reads, the improved customer service, and that sort of thing. So
yeah, and even to jump on that too, going back, Joe, you mentioned your college professors. One of the classes I had in college that I probably think about more than any now was the engineering economics, which was all about the life cycle costs and life cycle value of projects and technologies or infrastructure. And so one of the things that I've seen utilities when they're doing that ROI analysis is really going out to the full life of the assets. And so for AMI and large metering upgrades, we're looking at 20 years out. So if you're only looking at the first couple of years, you may be discounting, or you may not be thinking about it appropriately. But for a proper ROI analysis, I think you really should be looking 20 years out or 40. I've even seen some utilities go 40 years out. That's great. And then not only capturing the direct financial things, but then trying to incorporate the triple bottom line of the environmental and the social applications as well.
Okay, I know we have a lot more questions actually, and I assure you that we have record of them. So if we don't get to them today, hopefully someone can reach out to you via email and answer your questions. We did have one more about the cellular reader. Can the Ally meters be tied into the cellular reader? It's from John Decker.
I could take that one. So currently we don't have a way to connect the Ally meter to a cellular reader. Typically, on the census side of things, at least, when we are deploying the Ally meter, we're deploying it into that FlexNet network. But we do realize, there are cases where maybe you don't have coverage, or maybe you're an AMR customer, with a drive-by reading system. And so I know that is one thing that our residential product manager was kind of examining on that roadmap of different ways to improve the solution. So I'd say it's not available right now, but it's not necessarily out of the question.
And then I did have one question here to share the moderator's email, and that's me. My email is cheyenne@nrwa.org, and it's CHEYENNE@nrwa.org, and I'm just going to type it into the chat really quick in case anyone has any questions or needs a certificate or anything like that. Oh, whoops. And I believe we're going to have to end early, and I apologize for that, but I promise for all of you that do have unanswered questions, we will get back to you. And you guys have my email now. If you do need anything else, please do not hesitate to reach out. Thank you, Zach and Joe, for your time today. I really appreciate you and all of our attendees. If you guys like to say anything else.
Yes, thanks. Appreciate the time.
Awesome.
Thank you.
Well,
Yeah, I
thank
see
you
there's a whole
guys.
lot of questions here, and we look forward to getting back to you on some of these. Sorry we couldn't get the time here, but I see a lot of interesting questions, so looking forward to typing out some answers.
For sure. Well, thank you all and have a great rest of your day.